Welcome to The Explainer. Today we're going to crack the code of formal logic. We're going to take what looks like a totally alien language and, translate it step by step into something that makes perfect sense. Okay, let's dive right into our central puzzle. This thing, with all its arrows and symbols, definitely looks intimidating. So our mission, right, is to figure out if this thing is what logicians call a tautology. Basically, a statement that is, by its very structure, an undeniable truth. So how do we even begin to solve this? Well, you don't need a supercomputer or a PhD in math. All you really need is one single, master key, a key that unlocks pretty much everything in propositional logic. This arrow, this is the star of our show. It's called an implication, and it's just the logical way of saying if, then. It's super simple. If the first part, the antecedent, is true, then the second part, the consequent, has to be true as well.
And this is the secret sauce. This is the whole game, right here. The statement, if A, then B, is logically identical, the exact same thing as saying not A or B. This little trick is our master key. It lets us swap out those kind of tricky if-thens for much simpler or statements. Seriously, burn this into your brain because we're going to use it a lot.
Okay, let's grab that key and head back to our puzzle. We're going to use it on both sides of that main middle arrow and see what's really going on under the hood. All right, first up, the left side. Just think of the whole P and Q part as our A and R as our B. So we use our key. If A, then B becomes not A or B. Simple enough. That gives us not P and Q or R. Now, what does it mean to say not P and Q? Well, think about it. If I say it's not both rainy and cold outside, what am I really saying? I'm saying either it's not rainy or it's not cold, right? It's the same logic. So not P and Q becomes not P or not Q. And our final simplified version is just not P or not Q or R. Okay, now for the right side. We got to work from the inside out here. First, let's tackle that Q implies R. Using our key, that becomes not Q or R. Got it? So now our statement is P implies not Q or R. We just use our key one more time, with P as our A and that whole thing in the parenthesis as our B. And what do we get? Would you look at that? Not P or not Q or R. It's the exact same thing. So what's the big takeaway here? It's that these two super complicated-looking expressions, well, they're not different at all. They're just two different masks for the very same logical idea. They are 100% equivalent. Okay, hold on. This is huge. If both sides are identical, our whole crazy puzzle just collapsed. It simplified itself into a much, much simpler question. Is a statement that says, if A, then A, always true? Let's find out. And this leads us to a really core idea in logic. It's called a tautology. A tautology is basically a statement that's built for perfection. It's structurally impossible for it to be false no matter what you plug into it. It's just a universal logical truth. And here's where it all clicks together beautifully. Let's take A implies A and run it through our master key one last time. It becomes not A or A. Now just think about that for a second. Take any statement you can imagine. Like, the sky is blue. It's either true or it's false. So one of those two options, the sky is not blue or the sky is blue, has to be true. It covers all the bases. This means the statement is always true. It's a tautology. Puzzle solved. But, logic isn't just some abstract game we play with symbols. These rules are actually incredibly powerful for making everyday language super precise. Let's try to translate a simple sentence and see how it works. Okay, how about this sentence? Some real numbers are rational. Seems pretty simple, right? But how could we write this using the language of logic so there's absolutely zero room for misinterpretation? To pull this off, we need a couple of new tools. These are called quantifiers. And that word some in our sentence, that's our big clue. It tells us we need something called the existential quantifier, that backwards E symbol. It just means there exists at least one. Okay, now listen up because this is a fantastic rule of thumb that's going to save you so many headaches. That some quantifier, the existential one, it almost always teams up with the and operator. And the all quantifier, the upside down A, it almost always pairs with the implies operator. This is a super important pairing to remember.
So if we follow that rule, the translation becomes crystal clear. It reads, there exists something, we'll just call it x, such that x is a real number and x is a rational number. See? It perfectly captures what we meant. But think about why the other options are just wrong. If we used implies, the statement would be true for anything that isn't a real number, which is just nonsense. And if we used or, it'd be true for any number that's either real or rational. But that's not what the sentence is saying. Only and gets the job done.
All right, so let's boil all that down. What are the absolute key takeaways from our little logic adventure? Let's put our most powerful tools all in one place like a cheat sheet. Okay, it really comes down to just these 3 rules. First, that implication key. A implies B is the same as not A or B. That's your transformer. Second, the sum rule, the existential quantifier. The sum guy pairs with and. And third, the all rule, the universal quantifier. The all guy pairs with implies. Seriously, with just these 3 rules, you can take apart and build a staggering number of logical arguments. You know, these tools give us a blueprint for total clarity, for making perfect arguments, which kind of leaves us with one final big question to chew on. If we actually have these systems for perfect, unambiguous communication, what is it about us humans that makes our day-to-day conversations so often messy, confusing, and imperfect? That's something to think about.